Okay, what's up? Next 2 hours I'll try to give to Arduinoing because it's the weekend. And then I got my epic calisthenics workout. I'm technically the lowest I have ever weighted, so like 1.75 kgs. Yeah, that was what I weighed today. Pretty cool. I'm still not all of it, but I've still retained most of my strength, if not increased it over the span of an year. Because I used to weigh 82 kgs, I guess 1 year before this point, or 1 or 2 years, something like that. So anyway, feels pretty cool. Still going for that muscle up journey, but that's a completely different tangent. Look at this, we got the perfect Arduino setup. You like that? Oh my god, you like that cool parda behind me? That's, yeah, I got that. My mom got like rings to put. Anyway, yeah, it's like one weekend I'm free, the other weekend I will have something to do, so I've been pretty non-regular with this. My obsidian nodes have increased quite a lot. Like, look at this, holy shit. Like you just zoom out and it's starting to become look like something cool, right? Look at this is my grappling nodes, right? So much of them, and I have to update more of them now with my last few years, but I haven't really written it down. Like the entire book I read called Sapiens, I forgot a lot of it because I just didn't write it down, and that was one of the most like books that I read. So anyway, I have a mic attached over here. I don't know why I had this for a long time, but I just benched it. I did not use it. I'm using it today. I had problems putting it up with my Mac. So now what I can do is I can listen to any music in my earphones, right? Because you see how AirPods work usually, or any Bluetooth earphones, is that they can give all of the effort if the stream is one-sided, right? From just listening to music, nothing from the mic is going back there like in a voice call or in a stream, right? Music will be good quality, but the moment I turn to call or stream mode, the music quality becomes shit because now I'm listening to music and at the same time sending voice signals there. So the Bluetooth doesn't have enough bandwidth for it. So what you can do is you can just in your sound settings just disable the outgoing part. So now even during a call you can disable the outgoing part. So the other person won't be able to hear anything using these, but then the incoming bandwidth becomes epic. So now I can listen to high quality music. Even right now I have this Minecraft music on in the background. I'll try to pull it up. Yep, look, you cannot hear it on the stream because I'm not actually pulling in music from Opera into the stream, but yeah, I don't want a copyright strike, but just chill music. I find I'm able to work much better when I have something going on, like some music there to keep me in the groove. And so back to the point. If you disable outgoing, how will you actually talk to someone? You have an external mic for that. I had this for so long, I did not think about this, and now I take even for work, my Teams calls and everything, I take this way. And yep, it's pretty nice honestly, because this is actually it's just it cost 800 rupees something, but it works. Even a cheap mic gives pretty good voice quality, because it is a whole ass mic, not just something embedded in your device. And I'm not sure if you can see it here. Maybe I can try to. Yeah, you can't see it, but this mic is long. It's like a 10 feet cable or something like that to wrap it down, everything and shit. But yeah, aside from that, where were we? What I have to do now is to search Arduino, open the graph, super starter kit guide. We were on lesson 2, controlling LED with a button, right? Yep. So what we had learned before this was some concepts like what a button is, which is weird thing to learn from scratch, but yeah. Buttons are a common component used to control electronic devices. They usually use as switches to disconnect the circuit. Fine. Button jitter is also a thing. Each time you press the button, Arduino will regard you pressed it multiple times, because yeah, when you press a button why did that delete the whole line? I just wanted to delete the first character. What? Yeah, when you press a button, it's contracts do not close or open smoothly, rapidly for a few seconds. Cool. Software debouncing involves adding logic in the program. So initially you check if the button signal is low or high. Depending on the state, you introduce a delay and you verify the signal. If even after the signal the button state is the same, it was switched off or on. If the signal remains low or high, it's confirmed that it's if the signal has changed, discard the press as noise. Record this confirmed press as one action, right? Or you can do hardware debouncing using capacitor. Capacitor used to should probably make this a concept, right? Because I don't know much about these things. Used as a physical filter to smooth out the fluctuations caused by the buttons bouncing. Small capacitor. What was this called? New F something. Charges and discharges slowly, filtering out the rapid voltage changes due to bouncing. It's a stable signal. Oh, interesting. I still don't know how capacitors work, so yeah. Anyway, I will just make sure that the stream is going on smoothly. Yep. Anyway, I will just make sure that the stream is. What was this called? New F something. Charges and discharges slowly. Same. It was switched off or on. If the signal remains low or high, it's confirmed that it's if the signal has changed, discard the press as noise. Record this confirmed press as one action, right? Or you can do hardware debouncing using capacitor. Capacitor used to should probably make this a concept, right? Because I don't know much about these things. Used as a physical filter to smooth out the fluctuations. The audio is actually too good. I don't know why I haven't been using this, even though I bought it for the same reason. Yeah, this audio is nice. I should probably speak more clearly, but yeah, vocal skills. Okay. And the thing is, I don't even have an audio filter on OBS for this, so it's somehow just nice. Guess that's what mics get you. What if I stream like this? No. I mean, it does feel nicer because it's quite cold. Hardware interrupt to help the button talk to the Arduino. Signals sent to the processor by external hardware devices. Because the accessors this serve as a mechanism to modify the process even without requiring constant monitoring. polling. That needs to be a concept too. Why use Arduino interrupts? Tennessee checks or polls a device or sensor to see if an event has occurred. This wastes processing time, interrupts, executors, and only gets fine. So by this logic, a hardware interrupt also is a polling mechanism, just on a different line, which has less bandwidth or whatever, less processor time it takes, I guess. When the processor receives an interrupt, it pauses the currently running task. It saves the state of the current task. It executes this interrupt service routine, which handles the event. I should have coffee. After the ISR finishes, the processor restores the saved state of the previously running task and resumes execution. Fine. Is that all we learned about this chapter last time? I think so. Oh my god, I should honestly put the page where I am at currently, because this is just, Yep, key functions. Yep, we'll have to learn about these if I want to. Blinking LED also had a part where I stored Arduino functions, right? Fine. Arduino superstatic kit, no LED. We'll have to put key functions over here. Am I right? We'll just put the source of this as. Actually, we don't need a source here. We'll just delete it and put Arduino. Good. It doesn't need to be a date stamp because we'll keep updating the note. Next one is attached interrupt, ISR mode. Specifies a named interrupt service routine to call when an interrupt occurs. What is the named routine? Oh yeah, it showed that, right? And try to get any previous function that was attached to the interrupt. We have two external interrupts, number 0 on digital pin 2 and 1 on digital pin 3. So it has channels through which it can be interrupted. Interesting. Seems cool. So it has number 0 or digital pin 2, digital pin 2, and number 1 on digital pin 3. Cool. Possible. Shared sketch uses multiple ISRs. Only one can run at a time. The interrupts will be ignored until the current one is finished. As delay and Millis both rely on interrupts, they will not work while an ISR is running. The delay and Millis also rely on an interrupt. That's interesting. Not work while an ISR is running. Delay microseconds does not need to interrupt it somehow. See, they info bomb me with so much stuff in one paragraph that I have to make the connections then, and it's just a pain. Lesson 1. Now lesson 2, it was hardware interrupt. Firstly, I have to make this a concept. Oh my god, goddamn formatting. Right. And I have to add Arduino functions, the functions that we learned about, right? So the first one is attached interrupt. I hope I'm right. Attached interrupt. The ED is gone. Let's fucking go. Good joke. How many functions are there? Fine, I'll play the first one with this too. Kinda lame, but okay. These were all the functions that we learned about, and that we used in. No, that is not what I wanted to do. Obsidian. God damn it. Yep. Looping. Pin mode. Digital write. And delay. Right. These were all the functions we did last time. This time we have interrupts, attach interrupt. Let's just write them down first. We have digital read, which we did not already have. We have digital write. I have to check what that is again. Digital reads. Yes, not right anymore. Digital read and delay microseconds. Us. Interesting. Delay microseconds. Fine. These three we will be putting in. This looks so cool. Oh, this reminds me of something. Sometimes I'm happy I have two screens. Oh my god. Why did I have to show up on the stream? Now I cannot get it off the internet. Fine. It is on the stream now. What was up? Nah, nothing was up. Cool. Right, so let us learn about each of these functions together, children. Attach, interrupt, delay microseconds, and this. Attach interrupt specifies a named interrupt service routine. Call when an interrupt occurs. Okay. Specifies to call hardware interrupt occurs. Replace any previous function that was attached. Words of two external interrupts. Number 0. Short and fast. Well, I know a bit about those two words. Millis. Alternative does not use ISR. And I sometimes doubt that taking notes this granularly, if it's just an OCD thing for me or if it's actually gonna be useful down the line. I guess we'll find out, but I mean, nothing bad as long as I'm enjoying it, right? Delay microseconds. Okay, syntax is in ISR mode. Should have written the syntax here with the parameters. Oh, this becomes a line, which is quite cool. Pin is the pin number, of course. Function called takes no parameters, returns nothing. This function is sometimes 13. Change its value. Where is my boy? Hi. Honestly, listening to Minecraft music while doing this is kind of like, I feel like I'm learning redstone or something, except it's real-time redstone. I have noticed something throughout my life, like whenever you do stuff, even if you don't have any idea about what you're doing in the start, if you kind of stick with it for a while, like I've been trying to do with streaming and all, you build a very nice system around it. But if you try to go in with a nice system as the first thing, it won't happen. You'll run into too many problems. So I guess the way to do stuff is to first do it and then try to create a system. Because every hobby I've gone into it like that, I have ended up creating a pretty nice system for it. But yeah, I had to do it for that, right? back. Yes, so that was it about attach interrupt side. Hopefully app digital read is the value from a specified digital pin. The higher row, what was the voltage for the pin? $5. Makes sense that we have to read this time. Oh, we're getting to the good point. Quickly, number of digital pins you want to read. They don't give the code. What? Okay, they do give the code, they're just not posted it here. I'm done with 23 pages of this. Yes, a lot of them were starting pages. Thing with AirPods is that they kind of get dirty and then your ears start paining a bit after a while. Like, not paining, itching. It's still much better than headphones because headphones are just way worse for me. I am not comfortable with this metal container on me, it feels weird. Integer. I'm hoping we'll soon start with actually making the circuit, because yeah, that is microseconds. Interesting. No, but actually that's millions, right? Yep. 600 into 100. That is 16 milliseconds. Why is that though? This is not a children's book, right? Okay. the breadboard is vertical lines. All components in the line are connected. Provides battery to components to the power line, right? Yep. Okay. Finally getting to the circuit. What was this circuit like in yeah. The code folder. It's the only one where the code is there. Nope. Yep. Completely forgot I had to attach the Arduino too. But this seems to be the code. So I'll just write this here. Seems quite simple, honestly. Don't like how it spreads it around, but I know how to solve this. You do this .g/. So this is the command word for Vim. The plugin I have here, and see, easy. It's basically a Vim editor inside Obsidian, which is cool. Time to go check if my coffee is done. Yep, only thing with this mic is I have to replace it. But well, okay price to pay for quality, I guess. Okay. No sugar in this, but that's fine. Yep, let's understand this. We have the ground just connected here. We basically have a resistor which we're grounding for some reason. Completely forgot why we ground stuff. I hope this will be the longest part of the video, me trying to understand this. Fuck it, just ask GPT. Or just honestly, fine. Look at the code. Don't pamper yourself too much. So LED pin is 11 and 2. 11 and 2. Okay, let us take this to Excalibur. Excalibur. Right. Not this. Mackie, save me. There. And then we can also put the code right here. This is why I love Excalibur. Yep, see, side by side. So this line is setting this pin, right? Yeah. And PTN pin is this one. Should use a different color from these, otherwise it will just be a mess of stuff. Yep, the solar color 11 and 2. Fine. Set digital as the pin to control the LED. Set the digital pin to for the button interface. What is a volatile int? I love how I know when they're talking about this stuff, like registers, what they are, because I read a book about it. Let's go, big brain. Cool. We make a volatile integer and make it low. Defined output status. Cool. Not sure about this volatile business. Why this integer is here called state. Think it's just if the LED is on or not, but fine, we'll see. LED pin 11 is the output pin. And to the input, we'll have to check what pin mode means again. To act as inputs or outputs, fine. So number 11 will be the output at the starting, and 2 will be the input. Okay, so input is coming like this and going out like this. Seems about right. So if the digital reading from the button pen, which is 2, is low, detecting button interface to be low, which means the button is not powered, right? Delay 10 milliseconds. What was digital read again? Okay. If it's still low, then while the is low, delay 10 seconds. Why are we doing this twice? Ooh, you press it once and then it lights up, and then you press it again and it goes off. While button pin is low, keep delaying. That while loop will end when it is no longer low. We don't know how often the program checks that while or runs that while, which can be one weird thing, I guess, but okay. I don't know why we need 2 while loops. I'll play around with the code a bit. We're writing the opposite state in the LED pin. And the LED pin is this pin with a register. It can either be on or off. Don't know why it's going to the power strip here of the board. I have to build the circuit right now, that's the main part. I just don't understand this part, the power part, right? And this is all there is to the code. Quite simple. So it's time to use our overlord GPT. Copy. Oh my god, I did not want to paste that. T. I never wanna dance again unless I dance with you. Weirdly enough, I think singing is a hobby I'll never actually pick up. Let's see how that holds. Probably definitely starting an instrument before I ever think about starting singing. Explain. There's this whole business of this one 5-volt pin coming in. Explain circuits. I'm too dumb. Sorry. The circuit consists of an Arduino to an LED and a push button. Acts as a microcontroller to control the circuit. Okay. Push button input connected to digital pin 2, correct? Wired in a pull up configuration. The 10 kilo ohm resistor, one side of the button connects to a 5-volt power supply. Where is that happening? What? I'm not sure. Oh yeah, the button needs power to function, I guess. I'm not sure. I don't know. I think it does, yeah. Yeah, it does. So that is always giving power. Interesting. The power supply is always giving power. Why did I not think about that? And we manipulated using digital pins on and off. Interesting. I need to write that somewhere. The power, not the power shell. We don't like that. Not the power stack. Okay, whatever. The power supply. So the whole green thing is connected. And the whole this part is connected. Or just these. I don't know. Something like that, I guess. Will make sense if it's connected, right? Shows the input pin remains at high when the button is not pressed. To pin 2 and ground via the resistor. Why has it been grounded? is my question. Pin wide in CTs with a 220 ohm resistor, so it doesn't point the fuck out. Limits the current to protect the LED from damage. Yeah. One end of the LED connects to a 5-volt supply. I don't think so. Oh yeah. It's to ground. This same 5-volt supply is what I'm guessing that is. Is it? Maybe. Let me know if I have my questions. Questions. Why is a lot of stuff connected to ground? How is the 5-volt supply going into the button? The red wire connected to the black wire that is connected into the vertical strip of the breadboard. Why does the resistor after the button need to exist and before the signal goes to digital pin 2, and why is it also connected to ground? Fine. Second question I have is, how is the LED getting the power from digital pin 11? How is that pin providing 5-volt of energy, 5 volts are not energies, to the LED? Why is the other side is connected to a pin 2 and ground wire? The 20 ohm resistor. How are the black wires interconnected on the power strip? Reassembling the circuit without soldering. To the pull-up resistor. Why is not pressed? The pin is reading high. So it's getting current. Yeah, makes sense, I think. I don't know. I'm still having a hard time understanding the circuit. Where did my breadboard go? Here. Oh yeah, it does show plus and minus, look. In each vertical column. Oh. Okay, whatever, I'll just... For one thing, I'll just use this.
Channel. So for an example of how a breadboard would... Hi, my name is Ian Buckley and you are watching MakeUseOf.com. Today we're going to look at breadboards, what they are used for, and without any further ado, let's just jump in. Breadboards are used to prototype circuits. If you've got a starter kit with your Arduino or Raspberry Pi, you probably have one. They come in many sizes. For the most part, the standard large size and slightly smaller size are the ones you see the most, though some of them also come with binding posts for power sources as well. Regardless of which one you have, they mostly work in the same way. The bigger breadboards have lines running all the way down the longer side, which are known as the power rails. This is because you can plug your microcontroller or power supply into them to provide power to the components on the inside. Running perpendicular power rails, this is because they mostly work in the same way. The bigger breadboards have lines running all the way down the longer side, which are known as the power rails. This is because you can plug your microcontroller or power supply into them to provide power to the components on the inside. Running perpendicular to these are the component lines, and these are where you place your components. This is where you can build your circuit. Smaller breadboards work exactly the same as the larger ones, though they don't have the power rails running down each side. By flipping over a breadboard and pulling off the backing, you can see how they work. These pieces of metal run all the way along the board and connect all of the components together that you need. If you were to pull out one of the metal lines on your breadboard, this is what it would look like. They're all small metal crimps that are designed to grab the legs of the components. This is why they're so useful. It means you can make circuits without having to rely on learning how to solder or using a soldering iron, and it's very easy to prototype things quickly. One other feature of the breadboard that you'll see is that down the middle there is a channel, and this channel is a specific size and for a specific reason. The reason that it's there is because many integrated circuits or chips comply to a standard called dual inline packages. So for example here we have an L293D motor IC. This is designed for driving motors in a circuit, and as you can see it fits perfectly over that little channel. So for an example of how a breadboard would be used, let's look at a simple simple LED circuit with an Arduino. Here you can see there are two LEDs. One of them stays on all the time, and that's because it is being powered from the power rails of the breadboard, and those power rails are connected to the 5-volt and ground pins of the Arduino. You'll see that the other LED is blinking, and that's because it's been connected to one of the output pins of the Arduino, which is running the standard blink sketch modified to output on one of the pins instead of the internal LED. You'll also notice that the power rails running along the bottom side also work, and that's because at the end of the breadboard we have jumped the positive to the positive line and the negative to the negative line, and this is just a general good practice that it's worth doing because it means that your components will always have power. Is that the power rails running along the bottom side also work, and that's because at the end of the breadboard we have jumped the positive to the positive line and the negative to the negative line, and this is just a general good practice that it's worth doing because it means that your components will always have power no matter where they are on the board. Just before we finish, one little bit of trivia. If you're wondering why this plastic device that you have that helps you make circuits is called a breadboard, it harks back to the history of DIY electronics when people also wanted to prototype quick circuits, but they didn't want to have to get soldering iron out or anything like that. What they would do is they get an actual breadboard from their kitchen and they would use that with their components along with some screws or some nails or some thumbtacks to make quick circuits just to test things out or learn about electronics. So that is, in brief, what a breadboard is and what you can use one for. I hope this has been useful for you. As always, there is a full article on the Make Use Of website covering this. There'll be a link in the description for that. And thank you all so much for watching. Don't forget to subscribe to Make Use Of for more weekly tech tips and giveaways.
So it's just one whole line connected. This whole thing is the negative line. This whole thing is the positive line. Interesting. Back to GPT. Is the last one we made also? No, we did not use the power lines here, right? Yep. This one was very simple. This one is a jump in. Let's go back to the first one. And the button, okay, push button connected to digital pin 2. +5 connected to the positive, right? I could never.
Hi, this is going to be a very quick video that's a response to a question that I've got from a student, and the question was, when using a breadboard, do we have to have the positive supply up the top and the 0 volts down the bottom on our breadboards? And
side and the other, allowing breadboard, two things happen. First, they create a larger rail by connecting its two sides vertically, just like a ohm and a 1K ohm, and finally a LED. Let's start by connecting the power pins from the Arduino to the breadboard rails as usual. Next, place the button anywhere between the two sides of the breadboard. When you mount these 4-pin buttons on a breadboard, two things happen. First, they create a larger rail by connecting its two sides vertically, just like this. Second, if you click on the button, they establish a bridge between this side and the other, allowing any signal to follow through. Attention, this is a push button, which means they will only create a connection as long as you are pressing them. Now connect one of the sides of the button to the 5V rail. What we are trying to achieve here is to make the Arduino receive a high signal when you press the button and a low when you don't. As we will use pin 3 to read the state of the button, place a wire between the pin of the Arduino and the
Let's say you want to start designing your own synthesizer circuits. So you bought a breadboard and some components, but now you're having trouble figuring out how to use them properly? Then this video is for you. In it, I will walk you through the absolute basics, from identifying and handling components, understanding the breadboard's internals, to reading schematics, and then setting up your first simple circuits. Keep in mind that we won't dive into the theory behind those circuits. This video is strictly about the practical aspects of using a breadboard. Though if you're interested, I'm regularly doing circuit analysis videos on my channel. Before we begin, let's make sure we have all the necessary parts and tools. You can find a list of common starters items in the description. So obviously the star of the show is going to be your breadboard. And these come in different shapes and sizes, but I'm using a standard full-size variant with 830 tie points. And this will give us plenty of room to play around with. Next, we need some sort of power source. If you're just starting out, I strongly recommend you use 9V batteries here. 2 of them to be precise. This is because batteries will only get a little warm if you accidentally create a short circuit, whereas with a wall plug power supply, you might actually see things go up in smoke. To connect the batteries with our breadboard, we'll also need 2 of these simple clips here. Speaking of connecting things, a box of different sized jumpers can make your life a lot easier. These are basically just pre-cut solid core wires, so all they do is connect components on the breadboard. But often, that can really help clean up and organize your layouts. You could of course also just buy a big roll of wire and cut jumpers from it yourself, but for me, this is way more convenient. Since we're dealing with audio signals here, we'll also need a few jack sockets to get those signals into and out of our circuits. You can use 3.5mm ones if you prefer, but I'm going with big 6.35mm sockets. Now, in order to connect these with your breadboard, you've essentially got 2 options. If you're comfortable with a soldering iron, you could simply solder wires to the socket connectors. But in case you're not, you can always fall back on alligator clips like these. Just attach them to the connectors and to a small jumper, and you're good to go. This next tool is not exactly necessary, but it will save you a lot of headaches, especially while troubleshooting. A simple digital multimeter. With it, you can measure all kinds of things. The voltage between 2 points, or the amount of current flowing, or the resistance value, or even an oscillations frequency. Super useful. But okay, time to talk meat and potatoes. Here are some of the main components you'll be dealing with when building synthesizer circuits. First off, let's check our resistors.
I should have
the amount of current flowing, or the resistance value, or even an oscillations frequency. Super useful. But
I think I have a multimeter lying around somewhere. I was gifted to it by my uncle. printer right here. Don't think it's turned on. I have these clip thingies too over there. Look. Cool. Thank you, video man. I can use this. Interesting. This is fresh out of the box. Yeah, I have this whole screwdriver set. It has cells inside. I'm not sure if these batteries work. Oh, they do work. Let's go. I have a multimeter. I'm so happy. Never thought I'd be happy about having a multimeter lying around. Okay, cool. This thing kinda had a lot of dust on it. I need to clean it up.
Okay, time to talk meat and potatoes. Here are some of the main components you'll be dealing with when building synthesizer circuits. First off, let's check our resistors. These come in different physical sizes, which will roughly indicate their power rating. A bigger resistor can handle more electricity flowing through it because it dissipates heat better. With our use case, we'll rarely be pushing large currents through our resistors though, which is why I'm using these small and handy ones that can handle just up to 0.4 watts. Now you'll probably notice these colored rings across the resistor surface. Those tell you the resistance value, if you can decipher them. But honestly, I think that's too much of a hassle, which is why I normally just use my multimeter to determine resistances. For that, you simply have to set it to the resistance detection mode and hold each probe to one end of the resistor you want to test. As you can see, I've got a few set it to the resistance detection mode and hold each probe to one end of the resistor you want to test. As you can see, I've got a few 100k, 10k, and 1k resistors here. Now, these values are not going to be super critical, so if you've got some that are in the same
How do I connect it guys together? Hmm.
10k
Well, now
and
I
1k resistors
understand
here.
how to use
Now, these values are not going to be super critical.
I think I'm kind of understanding this. It's just a simple wiring thing. It's pretty nicely shown as black and white, so honestly don't feel like working out now because I'm kind of invested. Oh, this cannot go inside. That's what she said. Let me cook. Yes. This should be what goes inside. Okay.
For that, you simply have to set it to the resistance detection mode and hold each probe to one end of the resistor.
He has this one here. I don't know what any of these mean, honestly. Resistance detection mode should be there. I have to do this. I'm confused. Whatever, let's see if it gives any numbers when I touch it with one of my nice resistors. Which resistor wants to be sacrificed? Hehehe. Hoo hoo hoo. Hehehe. Here we go, my handy little packet of resistors. Give me current. Yep, it's off, I guess. Do you detect resistance? No, you don't. Yo, it has light. Epic. What are you used for? Fine, let's complete this video first.
This you want to test. As you can see, I've got a few 100k, 10k, and 1k resistors here. Now, these values are not going to be super critical, so if you've got some that are in the same ballpark, we should be good. Next, we'll look at capacitors. These can be a tad confusing, because there's a bunch of types that look wildly different. This here, for example, is an electrolytic capacitor. You can identify them by their cylinder shape and silver top. Foil caps, on the other hand, often come in this kind of boxy format. And ceramic ones have this round, knob-ish appearance. Now, with capacitors, you thankfully don't need to learn any color codes. Their value is usually printed right on the outside somewhere. So here, we have a 1 microfarad foil capacitor that can handle up to 63 volts. And this here is a 100 microfarad electrolytic cap that's rated for 50 volts. That voltage rating is important. Your capacitors can actually explode if you exceed it. But since we are only toying around with 9-volt batteries here, we're perfectly safe in that regard. And like with the resistors, the capacitor values are not that crucial, as long as you've got a few different ones to play around with. Next up, LEDs. These are probably self-explanatory. You can get them in different sizes and colors, and some of them can handle bigger currents than others. But apart from that, there's not much to look out for. Be sure to buy more than one though. You'll probably fry a few along the way. Still happens to me sometimes. Finally, we've got an integrated circuit here, or IC for short. ICs are basically like plugins. They serve a specific specialized purpose and encapsulate that in a handy little form factor. This one right here is a TL074, which has 4 independent op-amps on a single chip. You can use other op-amp ICs. This is just the one I have laying around in spades. Okay, so to get started, let's check out a very simple schematic. All this circuit's supposed to do is make an LED light up. There's 3 components involved: a power source, a resistor, and of course an LED. It works like this. Electricity flows from the battery's positive terminal through a current limiting 1K resistor and the LED, and then back to the battery's negative terminal, making that LED light up in the process. Now, in most schematics, you won't find the circuit laid out in a circular form like this. I just drew it this way because it's easier to read at first. In the wild, you'd probably see something looking more like the schematic over here. Semantically, these two are completely identical. We just separated the positive and negative terminal of our battery. This way, we can lay out our circuit in a more compact fashion. And once you look at more complex designs, you'll see how much that simplifies things. With this, we have all the information needed to build the circuit. The battery connects to the resistor, which connects to the LED, which leads back to the battery. But now the question is, how do we get it onto the breadboard? For this, we'll first need to understand how all these tie points are connected internally. So here's what we'd see if the breadboard was transparent. You'll notice that there's a clear and simple pattern. On the sides, we have what's called the power rails. These run all the way along the breadboard's length, connecting all these tie points together and are normal.
This is the kind of stuff I need to actually keep in my notes for later. Thank you, video man.
Normally used to distribute power to wherever we need it. And that's why they have these plus and minus labels, suggesting that we match them with our battery's terminals. Be careful though. Some breadboards will notice that there's a clear and simple pattern. On the sides, we have what's called the power rails. These run all the way along the breadboard's length, connecting all these tie points together and are normally used to distribute power to wherever we need it. And that's why they have these plus and minus labels, suggesting that we match them with our battery's terminals. Be careful though. Some breadboards split these rails into 2 isolated sections per side. And this is usually indicated by a gap in the red and blue lines like this, and can give you some mysterious power issues if you miss it. Next, let's look at our breadboard's middle section. This is split in half by this big rift, giving us 2 separate areas to work with. You'll see how that's useful later. Now, unlike with the power rails, the tie points serious power issues if you miss it. Next, let's look at our breadboard's middle section. This is split in half by this big rift, giving us 2 separate areas to work with. You'll see how that's useful later. Now, unlike with the power rails, the tie points in these sections are connected across the breadboard in chains of 5. So they run perpendicular to those power rails. Okay, so now that we know all this, setting up our circuit should be doable. First of all, I'll connect a battery to the power rails on this side using one of our clips. Now, all the tie points on this rail carry 9 volts, while this rail sits at 0 volts or ground. Looking at the schematic, we can see that this rail carry 9 volts, while this rail sits at 0 volts or ground.
So you can honestly, you don't have to follow the positive and negative thing, you can just do whatever.
Looking at the schematic, we can see that the only thing directly connected to the positive rail is the resistor. So I'll grab a 1K and stick it into one of the positive rail's tie points. It doesn't matter which one I pick, since they all connect to our battery's 9-volt terminal. Then, I plug the other end into one of the middle section's tie points. And again, I'm free to choose whichever I like best. This one seems appealing, so now this entire 5-point row connects to the positive rail through the resistor. Next up, we'll need to plug in our LED. There's a small caveat here. While for the resistor, the orientation does not matter, setting up an LED requires a little more care. And that's because LEDs only let current pass through them in this direction. How do we tell these 2 connectors apart then? Easy, you just have to check their length. One leg is always longer than the other, and that's the one that connects to our resistor. So I'll just plug it into the same row. Finally, the short leg needs to loop back to the ground rail to complete our circuit. And while you could just squish it past the resistor like this, I prefer to use a jumper to create a cleaner looking layout. To do that, I'll first connect the LED's short leg to a new row. Then from here, I can comfortably use a small jumper to link that row to the ground rail. And as if it's telling us we did everything right, the LED lights up. Great. Next, we'll tackle a slightly more complex circuit idea. This is a crude op-amp-based voltage inverter. The basic idea is this. If we apply a negative voltage here, the output LED will light up. And if we apply a positive voltage, it will turn off. Now, in order to be able to translate this into a breadboard layout, we need a bit more information. Information which is only implied in the schematic. Looking at the op-amp symbol, it's actually unclear how it's powered. We only see 2 inputs and 1 output. This is because the supply pins are only implied here. The schematic assumes that you know you have to power your op-amp. Sometimes people will draw it with the supply pins, but that's the exception. Okay, but how do you power an op-amp IC? Or any IC for that matter? Simple. You just Google your chip's name, in this case TL074, followed by the word pinout. This will most likely prompt you with what we call a pinout diagram, which shows you what each pin is for, and also indicates the supply connectors. If you're now wondering how to match your real chip's pins with the diagram, that's what this little notch is for.
This is too much for me now, so let's save this up till the point we've seen this, right?
Which you'll find in the diagram.
Okay, so too much mess on my thing here, but I like the idea of this. Anyway, I don't think I get to make this circuit today because, well, running out of time. God damn it, why did this have to be my hobby? Why can't I just do this all the time? Sadly, I have a job. But anyway, fun time only goes on for so long. I can do this for a bit longer, honestly. Should I? Yeah, I know what, screw it. I'll do it. I am considering if I should work out or not. I'm kind of invested in this. Whatever, I'll go work out. That's it for the stream, guys. I'll have to understand this thing again. Mike Skelly drawing. Hope it's staying. This guy will get banned from chat. Then I'll come by. Give me 5 minutes. So I understood that they're connected together, and I still don't understand how it goes from here to there. Kind of weird. Oh, it takes that route. So it comes here, then it goes there, then it comes from here. It's such a weird circuit, honestly. But I will have to do this next weekend, sadly. But actually, next weekend, will I be here? Yeah, I'll be here next Saturday. Spend time on this. there any kind of reminder that I can give myself for this? Not really. Fine. That's it for this stream, I guess. Thank you, arigato, Arduino-san. I learned a lot today, but I couldn't actually make the circuit because it's quite complex. So yeah, that is it. Thank you guys. Bye bye.